Hello everyone and welcome back to another video. Today we're going to continue our discussion of prime numbers, and specifically we're going to talk about prime numbers of special forms. In particular, we're going to focus on Mersenne and Fermat primes in this video. So to begin, the first type of prime that we're going to discuss is the Mersenne prime, and this is a type of prime that takes the form 2 to the power of n minus 1. And some examples of these type of primes, you could see, for example, 2 squared minus 1, and that's just 3. Or another example could be something like 2 cubed minus 1, which equals 7. But a counterexample, this isn't always a prime number. So these two are both Mersenne primes because they're prime numbers. However, this one, for example, 2 to the 4 minus 1, 2 to the 4 minus 1 is 15, which equals 3 times 5. So this is not an example of a Mersenne prime. So all of these are examples of Mersenne primes, and there's a lot of very interesting number theory and a lot of unsolved problems surrounding Mersenne primes. But in this video, we're just going to kind of start with the basics. We're going to discuss some of what's unsolved, but we're just going to start introducing them and explain the basics. And to begin, let's solve a polynomial long division equation. That's going to be very helpful for us in our first proof about Mersenne primes. For whether or not you guys remember polynomial long division, it works very similar to just like long division that you'd remember from elementary school. And what we're going to solve is x to the m minus 1 divided by x minus 1. And what we find here, well, we see what would we have to multiply x to get to x to the m? Well, you'd multiply it by x to the m minus 1. So then you can take x to the m minus x to the m minus 1, because that's what happens if you multiply x to the m minus 1 by x minus 1. So then subtract this, and what you're left with is x to the m minus 1 minus 1. Okay, so now we just keep doing this. So we do this again. We see that this time it's x to the m minus 2. That's what you'd have to multiply x minus 1 by to get to x to the m minus 1 minus 1. So this time multiplying by x to the m minus 2 is going to end us up with x to the m minus 1 minus x to the m minus 2. Then you subtract this again, and then what you're left with now is x to the m minus 2 minus 1. And I don't know if you're starting to see this, but there is starting to be a pattern. What happens each time after you do this difference, you add on a term that's one smaller, and then this x to the m minus 2 or x to the m, it goes down by 1, and you're just constantly adding on one term smaller. So let's do this one more time just so you can see the pattern again. So x, to get to x to the m minus 2, you'd have to do okay, hold up, I'm realizing I'm writing stuff weird. Okay, sorry, so it's x to the m minus 2. Sorry if that confused you guys. X to the m minus 3, so then you get to x to the m minus 2 minus x to the m minus 3, and then do the subtraction again. What are you left with? You're left with x to the m minus 3 minus 1. And this process continues and continues and continues. And eventually you reach the point where x to the m minus whatever is just going to be x to the 1 minus 1. And then at that point, you continue this addition. And at this point, you'll continue going down and then get to 1, where you just have to multiply x minus 1 times 1, and then x minus 1 you end up with remainder 0. So what you can say is that x to the m minus 1 divided by x minus 1 equals x to the m minus 1 plus x to the m minus 2 plus x to the m minus 3, continue on, all the way plus x plus 1. So to write this in a bit of a simpler notation, what this ultimately looks like, what we just found is that x to the m minus 1 over x minus 1 is the sum of k equals 0, m minus 1. And some of you might actually recognize this problem. This is actually the formula for summing a geometric series. We just used this long division method to derive that formula. So let's block this off. And then we can continue on. Okay, so with this result is going to help us make some sort of generalization about 2 to the n minus 1 as a prime number. So what can we say about these Mersenne primes when we have this formula? We see that there's some divisibility here by this 2 to the m minus 1. So we can see that there might be some implication about primes here, but let's go ahead and understand this. So this theorem is theorem 2.42, and the basics of this theorem are, or the statement of this theorem is, if n is a natural number, and 2 to the n minus 1 is prime, so it would be a Mersenne prime, then n must be prime. And even going back to the start, we can look at the Mersenne primes we just looked at, and we see, like, for these numbers that are prime, this number ends up being a prime. So these Mersenne primes correspond to a prime, but let's see if that generalizes. So for our proof, we're going to start by letting n be a natural number and let 2 to the n minus 1 be a prime. So this is a Mersenne prime. Now suppose, for contradiction, that n is not prime. And we're going to show how this leads to a contradiction, which means that the idea that n is not prime is absurd, so n has to be prime. Then n equals ab for some a, b in the naturals such that a, b is greater than 1. And this just directly follows from the fact that n is not prime. N has to be the product of two numbers, both of which need to be greater than 1. Thus, 2 to the n minus 1 equals 2 to the ab minus 1, which ultimately, we can just rewrite this as 2 to the a to the power of b minus 1. Now, remember from before, what did we say about these type of powers? If we wanted to divide this by 2 to the power of a minus 1, what would this yield us? Using this formula from above. Well, let's look at that. So note here, based on what we showed before, two to the a b minus 1 divided by 2 to the a minus 1 equals this sum. And 2 to the a k. So 2 to the a minus 1 divides 2 to the n minus 1. And note also here that a does not equal n because b has to be greater than 1. So a has to be smaller than n here. So these aren't the same number. But also, we know that we know that this has to be some integer, just because it's the sum of different integers. So basically, yeah, so you have this divisibility here. So since a is greater than 1, 2 to the a minus 1 is greater than 1. Hence, 2 to the n minus 1 is not prime, which contradicts the statement above that 2 to the n minus 1 is prime. So what we have here, we originally said 2 to the n minus 1 is a prime, it is a Mersenne prime. Then what we showed is that if n is not a prime, you can compose it as a times b, where a and b are greater than 1. So then what you can ultimately do, if you divide 2 to the n minus 1, or 2 to the ab minus 1, you divide it by 2 to the a minus 1, which has to be greater than 1 because a is greater than 1. You get this sum that ends up being an integer. So you can write 2 to the n minus 1 as the product of 2 to the a minus 1 times some integer. So I could actually... so this times that equals that. So that means that 2 to the a minus 1 divides 2 to the n minus 1. And that means, since it's greater than 1, 2 to the n minus 1 is not a prime, which is what we said. We originally defined it as a prime, so it has to be a prime. And this means, therefore, n is prime. So, looking at this proof, what exactly does this imply about Mersenne numbers? Or Mersenne primes? Well, what it means is that if you know that a number is a Mersenne prime, then the power of 2 that it's being taken to, right here, in order to produce the Mersenne prime, must also be prime. And as a result, when you're searching for Mersenne primes, you only need to test prime powers of 2, because each Mersenne prime necessarily involves a prime power of 2. So let's look at some examples of this again. Let's go back, similar to up here. Let's just look at some examples of these Mersenne numbers. So we have 2 squared minus 1 equals 3. Note that 3 is Mersenne, so 2 must be prime. And 2 is prime, like we see. That's not a good way of writing that. Okay. So this one is Mersenne, so this one must be prime. Now let's go to the next number, 2 cubed minus 1. That equals 7. 7 is a Mersenne prime. So 3 must be a prime, and we see that 3 is a prime. Next number, 2 to the 4 minus 1 is 15. This is not Mersenne. And as a result, 4 could be composite or could be prime. We see here that it's composite, and that's possible because that's not Mersenne. Now for the next one, 2 to the 5 minus 1 equals 31. And this is a Mersenne prime, so this has to be a prime. And we see 5 is a prime. Now, let's continue on because I want to show the first potential counterexample to this trend, because if you're looking at this so far, you might initially come to the conclusion that anytime 2 is taken to a prime number and subtracted 1, it produces a prime. But that's not always necessarily the case. Those would be examples of numbers that aren't Mersenne primes, where you're taking 2 to the power of prime, subtracting 1, produces a number, but that number is not a Mersenne prime because it's not a prime. So let's look at an example of that. Also note, we have to, it only shows, basically the point is that this only proves one direction. If n is a natural number and 2 to the n minus 1 is prime, then n must be prime. But the reverse isn't true. If n is prime, then 2 to the n minus 1 could be anything. It's not necessarily prime. So let's see that counterexample here. So 2 to the 11 minus 1 equals 2047, which equals 23 times 89. So as a result, this is not Mersenne. So 11 could be either prime or not prime. In this case, it's prime. In this case, it's a composite. But ultimately, the point is, if it is Mersenne, then the power that it's taken to must be prime. So that is that for that section. So that's what we have for Mersenne primes. The next topic that I want to discuss is the concept of Fermat primes. Let me just write. So the next concept that we have is the concept of a Fermat prime. And a Fermat prime is a prime of the form 2 to the n plus 1. So similar to before, except instead of subtracting 1, we're adding 1. Okay, so let's see some examples of this. Some examples of these types of primes could be like 3. 3 is 2 to the power of 1 plus 1. Another example is 5. 5 is 2 to the 2 plus 1. Another example is, well, let's just keep going. If we just go 2 to the 3 plus 1, this equals 9. That's not a prime. That's not a Fermat prime. Okay, let's do the next number. So this next number will be 17 equals 2 to the 4 plus 1. 17 is prime, so it is a Fermat prime. And then we can keep going. I'll just say 2 to the 5 and 2 to the 6 are not examples. But the next example would be 2 to the 8, which is 257. And then the next example is 655. 37 is 2 to the 16 plus 1. All these other examples in between, they don't end up being primes, so they're not examples of Fermat primes. to sort of start to generalize, the first thing that you'll notice is that it looks like the powers that you're taking 2 to are all powers of 2. That might be the first pattern that you notice. And that's ultimately what we're going to see about Fermat primes. We'll see, similar to like this thing, this theorem, if n is a natural number and 2 to the n plus 1 is prime, like what a Fermat prime is, then 2 must be taken to a power that is a power of 2. So like 1, 2, 4, 8, 16, 32 could be another example, continue on. And we'll see what happens when you go past 16 later on, but the general thing that Fermat noticed when he sort of discovered these primes is that when you take them to powers of 2, add 1, that's when you discover that you produce these primes. Now, before we prove that theorem, one thing we're going to need to look at is the binomial theorem, because I use that in my proof here. And the binomial theorem simply states x plus y to the power of n equals the sum of n, and then k equals 0, and then it's n, choose k. And this is a combinatorial notation for something. A to the k, b to the power of n minus k. And I believe that the combinatorial thing is just over so yeah, but the basic point here for this symbol, it basically refers to the amount of ways to choose k of something when you're choosing out of a total of n, basically. It's the amount of ways, like you're drawing from a hat to make k selections without order when you're drawing from n possible selections. But the reason why that matters, but let's go through and prove this theorem just very quickly. The combinatorics is not the main subject of this video, but I do end up using this theorem, so I do want to just give a very brief proof here. For this proof, this is going to be a combinatorial proof, which basically means is a proof through counting. You're proving that each side of the equation is counting the same thing. And you're going to use this choose notation to count how many times you're going to choose x and y from this. And I misstated this theorem slightly. Sorry. It's ultimately the same thing. I just wrote it as if there was a and b right there. But so we're going to write x plus y to the n as the product as a product of factors and this is just a product that's taken n times. And next what you're going to do is expand and collect like terms. And then each term in your future formula is going to arise by choosing x or y from each factor. So you're going to go into each of these factors, and when you're multiplying them out, you choose x or y, choose x or y, choose x or y, choose x or y n times. And then before you collect these as like terms, since you're choosing between one of two options and you're doing that n times for n of different factors, so here you're gonna have two options. Here you have two options, and you have two options n times. So you take two. So to see the amount of terms that you're gonna produce, it's 2 times 2 times 2 n times. Because you're choosing x or y, that's two options, then choosing x or y, and those kind of stack, and then you ultimately have 2 to the n options. So, so before you collect like terms, there are 2 to the n terms. Each term has the form n to the x to the n minus k and y to the k, because you have n different terms, and then say you choose y k times out of that, then you have to choose x n minus k times. Okay, x to the n minus k, y to the k means that we choose, or means that we chose y from exactly k of the factors. So we go in here, and in exactly k of these factors, we choose y. The other n minus k, we choose x. Now remember how we defined this n choose k before. You're going into a set of n things and choosing from those n things, you're choosing something k times, basically. You're choosing k of something from those n factors. So if you go into these n factors, you're choosing k of them where you pull y out. So you're going in there, choosing k of them, and the order doesn't matter. Like that, the order in which you choose, like if you choose the first one to have y first and then choose the second one, that's no different than choosing the second one first and then choosing the first one, because in both cases the first and second are going to appear. So you're going into these n factors and choosing k of them where y is the one that you're choosing, basically. So x to the n minus k times yk means we choose y from exactly k of the factors. And this occurs n choose k times, since there are that many ways choose y from k factors. Hence, x plus y to the power of n equals n, k equals 0, and choose k, x to the n minus k times y to the k. Okay, there we go. I was looking at old notes when I wrote this, so I originally wrote it like with a's and b's in the solution, and then with the original term being x and y's. So I had some weird inconsistent notation in the proof that I wrote, but this is all consistent now. Yeah. Okay, so this is basically the proof. It's a combinatorial proof. If you've just been following along with the number theory series, you might not fully understand why the n choose k works exactly how it does. But for that, I'm planning on eventually making a series on combinatorics on this channel after I start getting through this number theory series. So hopefully, if this piqued your interest, if this type of proof piqued your interest, it's honestly one of my favorite types of math is combinatorics. So yeah, get excited about that type of proof and that type of content, because you should expect it coming sometime in the next couple of years on this channel, or someday on this channel I'll post some combinatorics. But with all of this in mind, this is a bit of a side point to the main video, but we're going to ultimately use it in our proof about Fermat primes. So let's look at, and this kind of can also help show you how different fields can be helpful in math as they overlap. So theorem 2.43. If n is a natural and 2 to the n plus 1 is prime, then n must be a power of 2. Okay? So what we're going to do for our proof, going to be a very similar looking proof to our last one, but so we're going to let n be a natural such that 2 to the n plus 1 is prime, and for a contradiction, n is not a power of 2. All right. Now, since 2 is the only even prime, and every natural is a product of primes, by FTA. Every number that is not a power of not a power of 2 is divisible by an odd number that is not equal to 1. And to understand this point, think about these natural numbers in terms of their prime factorization. If a natural number is not a power of 2, then there must be some other prime in there. Otherwise, it would just be powers of 2. You would have to add in some odd number to the primes, because the only even prime that you have an option for to choose is 2. And if you keep adding in powers of 2, or adding in 2, it just becomes a larger power of 2. The only way to make it not a power of 2 is to put in some odd prime into that prime factorization. So as a result of this, thus 2 to the m plus 1 divides n for some natural m where m is greater than or equal to 1, so that 2 to the m plus 1 is greater than or equal to 3. Because if m is 0, for example, then 2 to the m plus 1 is just 1. But as I said before, this number that it's divisible by must be greater than or equal to 3. It can't be equal to 1. It has to be divisible by something that's not equal to 1. All right. So then, hence, 2 to the m plus 1 times a equals n for some a that's a natural. Also note that a has to be greater than or equal to 1 because 2 to the m plus 1 cannot be greater than n, basically. Because otherwise, how would it divide n? And then additionally, a has to be less than n because 2 to the m plus 1 is greater than or equal to 3. The only way for a to equal n would be if 2 to the m plus 1 equals 1, but that's not possible. Okay, so next we're going to let x equal 2 to the n plus 1. Oh, why did I do that in that proof? That doesn't make sense. I don't know why I did that. Now, the next thing we're going to do is just a bunch of algebra. So 2 to the n plus 1 equals 2 to the 2m plus 1 a plus 1, which equals 2 to the a to the power of 2m plus 1, which equals 2 to the a plus 1 minus 1, 2 to the m plus 1 plus 1. Okay, so now we have this written out in a way that we can perform a binomial expansion on it. We can use the binomial theorem. So what we can do now is write this out with the binomial theorem. So that equals sum 2 to the m plus 1, I equals 0, and then 2 to the m plus 1 I, and then 2a plus 1 to the 2m plus 1 minus I, and then negative 1 to the power of I plus 1. It's a very long, but this will ultimately reduce down and make it so that we can prove what we're trying to prove. Sum 2m plus 1, and then I equals 0, and then, oh, no, what we're going to do now is factor out a 2a plus 1. And what is this going to do? So let's take out this 2a plus 1. But one thing to note is that when the term is 2m plus 1, we won't be able to do that. So we'll have to split that out at the end, split that out as an extra term at the end. And we'll see how we do that very soon. Okay, so we pull that term out, so it gets rid of that plus 1. But then at the very end, we're going to have to add back in that term for the 2m plus 1 part at the very end, where we have 2m plus 1 over 2m plus 1, and then 2a minus 1 to 0, and then negative 1 time to the power of 2m plus 1 plus 1 at the very end. Okay, so what happens with this last term? Well, for this last term, the only way to choose 2 to the n plus 1 terms from 2 to the n plus 1 set is just the one way. You just choose them all. So this ends up reducing to 1. And you can see that even from this theorem, if you just have n over n, it ends up being n factorial divided by n factorial times 0 factorial. So it'd be n factorial over n factorial times 1, which is just 1. Anything to the power of 0 is just equal to 1. So this is just 1. And the negative 1 raised to any odd power is negative 1. So all of this, multiply 1 times negative 1, changes into negative 1. And that actually ends up canceling out with this 1 here. So let's see that worked out. And note that I got rid of this plus 1 here because that very last term is being pulled out here to the very end. So plus negative 1 plus 1, and then ultimately it all just becomes 2a plus 1, and then 2mi equals 0, 2m plus 1 over I, choose I, 2a plus 1, 2m minus I, negative 1i. Okay, so what did we just show? Why does any of this matter? Well, what we have here is we have 2 to the a plus 1 times some integer. This is complicated, but ultimately the point here is that this is just some integer. Because what we've just shown here is that 2 to the a plus 1 divides 2 to the n plus 1. And a, we know, is less than n. A doesn't equal n. So these aren't the same number. And also it has to be greater than or equal to 1. So 2 to the a plus 1 must be greater than or equal to 3. So 2 to the n plus 1 is now divisible by a number that's between 3 and n minus 1. It's not 1 and it's not n. 2 to the n plus 1 is divisible by this number. So that means 2 to the n plus 1 is not prime. However, remember at the very beginning, we defined that 2 to the n plus 1 has to be prime. And the only reason that it isn't is because we said that n is not a power of 2. Well, n not being a power of 2 leads to a contradiction here. It leads to the contradiction that 2 to the a plus 1, or 2 to the a plus 1 divides 2 to the n plus 1. So let's just write this out. And 1 is less than or equal to a is less than n. Oh. So 2 to the n plus 1 is not prime. A contradiction. Hence, n is a power of 2. And this ultimately means that for all Fermat primes that take the form 2 to the n plus 1, over here, for all Fermat primes that take the form 2 to the n plus 1, that n must be a power of 2. Now, Fermat originally hypothesized that all numbers of the form 2. So basically a Fermat prime, instead of being just simply 2 to the n plus 1, it would be 2 to the 2k minus 1. And Fermat hypothesized that every single number of that form is prime. This is not true. Ultimately, Euler refuted this. So remember before, we have this really good pattern going so far. Like 2 to the 0 plus 1 is 3. That's prime. 2 to 2 to the 1 plus 1 is 5. Prime. 2 to 2 squared plus 1 is 17. We have another prime. 2 to the 2 cubed plus 1 is 257. Another prime. 2 to the 2 to the 5. Or, wait, that is 2 to the 2 to the 5, right? No, 4. 2 to the 2 to the 4 plus 1 is 65,537. However, now is when we're going to talk about 2 to the 2 to the 5. And that is 2 to the 32. And that number is... Oh, wait, let's do this. Let's talk about 2 to the 2 to the 5 plus 1. And that number is 2 to the 32 plus 1. And that number is 429467297. I hope I wrote that down right. But we're looking at this number is equal to 241 times 6700417. So what we see here is that this number actually is not prime. In fact, the only Fermat numbers, the only Fermat primes that we know of are these 5 numbers: 3, 5, 17, 257, 6, 5, 537. We haven't found any others. We don't know if that there are no others, by the way. That's an unanswered question that we're going to talk about later. But those are the only ones that we've found so far. So with all of this in mind, we can finally look at the way the book defines these prime numbers. They wait till the very end to define them. So the definition, 2 to the p minus 1, where p is a prime, of the form 2 to the 2 to the k plus 1 is called a Fermat prime. Now, with all of this in mind, let's talk about a few other things. Let's talk about some of the unsolved problems now. So we have these concepts of Mersenne primes and Fermat primes, but despite how simple some of the actual formulas for them are, 2 to the n minus 1, 2 to the n plus 1, there are still many, many, many unanswered questions out there about them. For example, very simple question. We answered this with primes just a few episodes ago. How many are there? How many Mersenne primes are there? How many Fermat primes are there? Well, with regards to Mersenne primes, we've found about 52 of them, which doesn't seem like a lot. There's a lot of numbers out there. And then with regard to Fermat primes, we've only found 5 I've listed all the Fermat primes that we know of. But despite this, we don't even know if they're finite or infinite. There could be more Fermat primes out there. And I don't know how likely that is, just given how few that we found. But there could be more out there. Mersenne primes, there's almost definitely more out there. It's just computational power isn't able to find them yet. But we found 52 so far. But we've never proven that there's a finite number, never proven that there's an infinite number. There's nothing that we've proven yet. Additionally, there's a very interesting area of unanswered questions with regards to the connection between Mersenne primes and perfect numbers. And there's a whole Veritasium video on this that's really interesting. So a perfect number is just a natural number whose divisors besides itself sum to equal itself. So let's look at some examples. Factors of 6 are, so 6 is the first example. 1, 2, 3. Well, 1 plus 2 plus 3 equals 6. 6 is also a factor of 6, but they exclude that. I think the idea, the actual definition would be like a proper factor of 6 or something like that. Those factors sum up to equal 6. Additionally, factors of 28 are 1, 2, 4, 7. Well, 1 plus 2 plus 4 plus 7 equals... No, it doesn't. Oh, sorry. I forgot 14. Okay, sorry. Factors of 20. I think I forgot to write down the 14 in my notes, and I was like, wait, that doesn't make sense. Okay, but it's 1, 2, 4, 7, 14. And you add those up, those equal 28. The next two examples of numbers are 496 and 8128. Now, one thing that we actually do know about these perfect numbers is that there is a deep fundamental or foundational connection between them and Mersenne primes. And this is expressed in the Euclid-Euler theorem. An even number is perfect if and only if it has the form two to the p minus 1 and then 2 to the p minus 1, where 2 to the p minus 1 is a Mersenne prime. So proving this theorem happened in 2 steps. Euclid proved this direction. Euclid basically proved that if a number has the form 2 to the p minus 1 times 2 to the p minus 1, where 2 to the p minus 1 is a Mersenne prime, if you guys are listening to this, you won't understand the difference between what I just said, but I also don't know how you would listen to a math proof video. That doesn't make sense. if a number has the form 2 to the power of p minus 1 times 2 to the power of p minus 1, where 2 to the power of p minus 1 is a prime, then it is an even perfect number. So Euclid proved that direction. But ultimately, he didn't prove the other direction. That, you had to wait a couple centuries for that, for when Euler came around. And Euler proved the other direction. So he's basically proving if a number is an even perfect number, it has the form 2 to the power of p minus 1 times 2 to the power of p minus 1, where 2 to the power of p minus 1 is a Mersenne prime. And this theorem establishes this very foundational connection between even perfect numbers and Mersenne primes. And you can see this if we just go ahead and list the first 5 perfect numbers and first 5 Mersenne primes. So let's just write out this table. 1, 2, 3, 4, 5. And then we'll do the prime numbers that we're going to use here. It's going to be 2, 3, 5, 7, 13. Because remember, 11 doesn't work. And then what we'll look at next is the Mersenne prime, 2 to the power of p minus 1. And then we'll look at the perfect number, 2 to the power of p minus 1 times 2 to the p minus 1. Okay. So this one is 3, this one's 7, this one's 31, this one's 127, and then this is 8,191. And then next, the perfect numbers that correspond to it are 6, 28, 496, 8,128, and then 33,550,336. Now, the important thing to note here is that these are the first 5 Mersenne numbers on the left, and then on the right are the first 5 perfect numbers. So there's this very foundational connection between the even perfect numbers and the Mersenne primes. But once again, since we don't know that there's whether or not there's infinitely many Mersenne primes, we also don't know if there are infinitely many even perfect numbers. We don't even know that all perfect numbers are even. It's completely possible, though not likely, that there are odd perfect numbers out there. All that we've seen so far, every single one that we found so far, is even. But there could be odds. There's no disproof of that yet. And all of these questions, just thinking about all these types of primes, all the questions here, there's so much room for advancement in number theory on these subjects. And if you could answer these questions, you, the viewer right now, if you can answer these questions with proofs, you do need very good, rigorous proofs, you would very likely receive the Fields Medal. Like, these are ancient problems. Like, they go back all the way to Euclid, and they're still unsolved. There's still so many questions about them. There's still so much time that needs to be spent to answer these questions, that they just haven't been answered yet. So yeah, go ahead, send the proof, post in the comments down below when you have time. Good luck. Best of luck to you on solving these generational questions. But with that, I'll open up to the comment section. Thank you all for watching. If you liked the video, go down and hit the like button. If you want to be notified of future content, go subscribe. If you want to support my channel, there's a Patreon down below. And if you want to participate in the community, ask me questions, there's also a Discord link down below. But with all that, thank you all for watching, and I hope to see you all in the next video. Peace.